So in this section, I want to go through the theory of a nozzle. So we'll start with a pump. The pump is a steady flow device, meaning that the flow rate remains constant over time. When you switch it on, there's a short period of time where it ramps up, and then eventually the flow rate reaches a steady rate, unless you change something, unless you change the speed of the pump, the motor that's driving the pump, or you adjust an outlet valve. Now, in a steady flow situation, the continuity equation tells us that the volumetric flow rate in meters cubed per second is a product of the cross-section area in meters squared by the velocity in meters per second. And that's how we get meters cubed per second. So in a steady flow situation through a pipeline, if we experience a sudden contraction in the pipe and the area reduces, according to the continuity equation, the velocity must increase and vice versa. And that's the basic theory of the nozzle. The Bernoulli principle states that an increase in velocity leads to a decrease in pressure and vice versa. So velocity and pressure are inversely related to each other. So what we have then, as when the velocity increases, we have a minor pressure loss. And this is our minor loss equation. Now, when we come to a situation where we have a sudden contraction in the pipe, we'll see that there's two velocities here, an upstream and a downstream velocity. So which one do we take in our minor loss equation to calculate that minor loss? The rule is we always take the largest one and err towards the greatest loss. It's better to overestimate your losses than underestimate your losses. So if you have a pipe network and you work out all the losses associated to that pipe network, you can then specify a pump big enough to overcome them losses and provide a pressure and a flow rate at the end of it to do what you want it to do. If you underestimate those losses, then that pump may not be able to do what you expect it to do at the end of that pipe network. So that's why we always err towards the greater loss. So you take V2 in this case, in this sudden contraction situation. So the nozzle simply is a device that increases the kinetic energy, in other words, the velocity of the flowing medium at the expense of its pressure. We do that by reducing the cross-section area. So let's say you have your outlet pipe designed like this, but it doesn't have a nozzle at the end. What you do is you work out all your major and minor losses in that outlet pipe over a range of flow rates, and you produce your pipe characteristic curve. You then superimpose your pump characteristic curve, and where they intersect is the operating point. And drop that down onto the x-axis, and you'll get your flow rate, your volumetric flow rate that system is providing. So in this equation, you've got your volumetric flow rate, you've got your cross-section area based on that 8 mil ID tubing that you're using, and from that you can calculate your output velocity. The output velocity will feed into this equation to help us calculate the velocity of the boat moving through the water. It's basically Newton's second law of motion. Force equals mass by acceleration. And that equals the propulsion of force of the boat that's provided by the pump pushing it forward, minus the drag force that's provided by the water resisting the movement of the boat going through the water. So ultimately what we're going to do is calculate this acceleration, and from that calculate the velocity of the boat as it moves through the water. So what we want is we want a large propulsion force and a small drag force. So what feeds into calculating the propulsion force is the velocity that we're getting from our pipe network. So can we increase that output velocity? Well, that's where the nozzle comes into play. So let's say you create a nozzle that brings the diameter down to 6 mil. It's going to have a minor loss associated to it. You calculate that minor loss over a range of flow rates and update your pipe characteristic curve. So you go from the blue line here to the gray line that I've labeled 6 mil nozzle. What you'll see is that your volumetric flow rate your operating point moves backwards, so your volumetric flow rate moves backwards, and you've a new lower Q value. You've also got a new cross-section area based on that 6 mil, and you recalculate your velocity. What you should find is that that velocity increases. So you're in theory, you're getting more propulsion. You can do the same thing for a 4 mil nozzle and a 2 mil nozzle, and each time you recalculate your new velocity, and you should see it increase. So in theory, that's giving us more propulsion. However, in this equation, we also see that m dot, the mass flow rate, is a contributor to propulsion, and m dot is the density by the volumetric flow rate in meters cubed per second. So as we introduce a nozzle and increase the velocity, we're reducing our volumetric flow rate and reducing our mass flow rate, which at some stage is going to actually start working against us and giving us less propulsion. So what you need to do is you need to examine the effect that a 6 mil, 4 mil, and 2 mil nozzle has on the propulsion. At what stage does it increase and then start to decrease the propulsion? So if you have, for example, a 1 mil nozzle, what you're doing is you're putting a severe restriction in the flow of the fluid and reducing your mass flow rate and reducing the thrust in the boat. So somewhere along that line, you're starting to affect the thrust, and that's what you need to examine. So when it comes to designing your outlet pipe and identifying the K factors, you would have a minor loss at the inlet and the outlet. So you could take a K factor at the entry of 0.5 and at the exit of 1. You'll have a number of 90-degree bends. You could take a K factor of 0.75 for them. And then for your nozzle, you'll need to determine the K factor for that nozzle. So there's some information in the theory section about K factors. It touches off the nozzles here, but there's a more comprehensive formula that I took from a technical paper from the Crane company. And so you've got this equation here. You can use the top version if your included angle is less than 45 degrees, and the bottom version of it if your included angle is more than 45 degrees. So you more than likely use the top version. So the beta value is the ratio of your diameters. So you're going from maybe an 8 mil diameter tubing down to possibly a 6 mil or a 4 mil here. And then the theta then is your included angle here. So it should be handy enough to calculate a K factor for your nozzle. Then you draw it up and you can print it then on the 3D printers. So I mentioned about the water line previously. You have to make sure that that inlet pipe is below the water line so that it gets primed and flooded with fluid, so that it works. So in this particular case, it's too high going over the back. It's unlikely to be able to be primed. In this case, you're just about getting away with it. Some teams in the past have experimented with the position of the inlet pipe in the sense that they've taken the fluid in from the front and they've expelled it out the back. See a couple of versions on that. The problem is when it comes to the theory, which I'll cover in the third and final stage, the propulsion force, the equation tells us that if we take the fluid in from the back and out the back, we're maximizing the velocity effect. So we can add the two velocities together and give us more propulsion. In the other case, if we take the fluid in from the front and out the back, then we take one velocity away from the other. So there's less propulsion in that case. And if we take the fluid straight up from the bottom and out the back, we can neglect the inlet velocity. So once again, less propulsion. So the maximum propulsion is provided by a situation where we take the fluid in from the back and expel it out the back. This feature will also add as an obstruction to the hydrodynamics, and then it might push our boat off to the left or right. We've had some groups experimenting with these outlet pipe designs like this. The problem is that we, strictly speaking, are working with straight sections and 90-degree bends, and we can work out the major and minor losses for them. But these situations, they're neither straight sections nor are they 90-degree bends. They fall in between the two. And what the closest they come to is what we call a large radius bend. And we don't have a K factor for them. But if you want to experiment by using ANSYS or Fluent and to see if you can come up with a K factor for a situation like that, I'm all for experimentation. And just in your presentation, talk about how you conclude the K factor for a design like that.